In 12.1c, let's construct and interpret a confidence interval for the slope of a population regression line. So what we're going to do for the slope is, in this one we're going to actually use a t interval, as we would use the t statistic for any type of quantitative data, keep that in mind, and it's for the slope of the least squares regression line. Once the conditions are met, remember the liner conditions, and we've defined our confidence level to use for our interval. Here's the calculation. You're going to take the actual estimated slope from your sample. So remember, lowercase means from your statistics. So this is the sample slope plus or minus your t critical value, and then we're going to times it by the standard error of the slope that we just looked at on the previous lesson. And remember, this was the standard error of the slope, which is on the formula sheet. Now, on the formula sheet, you're also going to find a few other things. This S of x, if you forgot what it was, the standard deviation of the x, is on the formula sheet and it's listed right here. Do know that the standard error for the slope is also listed on the formula sheet in a different format. What you could possibly also see is it being reported in this format. It's pretty intense, but really all that this is doing, it's the same two formulas. All it does is, instead of recording S as a standard deviation of the residuals, it actually puts the standard deviation of the residuals formula there. And then instead of just doing the standard deviation of X, it actually is going to put that there and simplify the denominator of this particular formula. So you will see both of these on the formula sheet. Again, I've never really referenced this one, but do know it's there. Now remember, in this one we are going to be using the t interval, or that means the t statistic. And when you do anything for t distributions, you must talk about degrees of freedom. So when we did the previous chapters, when we looked at one sample or two samples, our degrees of freedom was always a sample size minus 1. Well, we are doing bivariate data now, so your degrees of freedom are a little bit different. Make sure for anything for regression analysis or slope analysis, degrees of freedom is n minus 2, so your sample size minus 2. Let's go back to the seat location and your test score. Again, here's our scatter plot, and it's our computer output that we already saw. For part C here, they want us to identify and interpret the standard error of the slope from the computer output. Now remember, our slope value is right here for the row, so I'm just going to go ahead and notice that it says SE coefficient. So the standard error for the slope is actually this value right here. If we interpret that in context, what we can say is this. We would say that 0.9472 is the number, and if we repeated a random assignment many times, the slope of the estimated regression line would typically vary by about 0.9472 from the slope of the true regression line for predicting the test score from the row number. So this number just reports how much our slope could actually vary, though, if we were to take different random samples and compute another slope from that. There's some error in our current slope. Now, one thing about the computer output I do want to highlight, again, I already said we don't use the adjusted R-squared. They are absolutely going to recommend that you don't reference the test statistic in here, and we'll talk about that again further when we get to looking at that component. Now, part D is going to ask us to compute the confidence interval for the slope. So what we're going to want to get from that before we move on to the next slide here is to actually get the slope value from our particular sample. We want to make sure we've recorded the standard error of the slope, so we have those two values. We are going to have to compute our critical value, so let's just take these two values with us onto the next page. So for the confidence interval, remember the formula is going to be taking our b plus or minus t critical value and then the standard error of our slope. We found these two values on the previous slide, so now we have to compute our critical value. To do that, we're going to do just like we have with t distributions, either use the t table or inverse t in our calculator. They want to be 95% confident, so remember, for our 95% confidence interval, we're going to have a remainder in here of 0.025. So to compute the actual test statistic that sits right here, we have to use the area of 97.5%. The degrees of freedom are going to be this. We need to take, for this case, our sample size minus 2, so use 28. So do an inverse t of 0.975, 28 degrees of freedom, gives us this critical value. So we can use 2.048 in this element here. Let's go ahead and do that, and when we do, what we're going to get is plugging our various information in and simplifying, we will get our final confidence interval for the slope. Now interpret that in meaning. In context, what that means is this. We are 95% confident that the interval from negative 3.057 to 0.8228 captures the slope of the true regression line relating the student's test score y and the student's row number x. Last question here. Based on your interval, is there convincing evidence that seat location affects your scores? Well, if your scores were unaffected, what number would that be? The score that would indicate an unaffected evidence would be the score of 0. It means it didn't make any difference. So the question is the number 0 included in this confidence interval? And it is. Therefore, we can say, because the interval of plausible slopes includes 0, we do not have convincing evidence that there's an association between test score and row number. Again, make note of the one thing I already talked about. They recommend, the AP board says, when you're looking at the computer output related to slope, the test statistic that is listed should not be used for that. So the t values, please do not use those. We need a computer own, like we just did, back for the confidence interval. Look at another example from start to finish. Fresh flowers. 2 AP Stats students decided to investigate the effect of sugar on the life of cut flowers. They went to the grocery store, randomly selected 12 carnations. All the carnations seemed equally healthy when they were selected. When they got home, students prepared 12 identical vases with the same amount of water. They put 1 table of sugar in 3 vases, 2 tables of sugar in 3, 3 tables of sugar in 3, and the remaining 3 with no sugar. After the vases were prepared and placed in the same location, the students randomly assigned 1 flower to each vase and observed how many hours that the flower stayed fresh. We've seen this data before, so hopefully it rings a bell to you. This right here is a scatter plot of the tablespoons of sugar and how fresh the flowers lasted in terms of hours. Here's our residual plot, and here's the frequency histogram of our residuals. The computer output from their analysis shows us this. Here's the standard error of the residuals, right there. Here is our y-intercept, here's our slope, and here's the standard error of the slope. If we need it, there's our r squared, in which we can also use to compute our correlation, or r. So let's go ahead and compute a 99% confidence interval for the freshness of the flowers related to their sugar. On the state portion here, what we would say is that we want to estimate the slope b of the true regression line relating hours of freshness y to the amount of sugar at a 99% confidence level. We need to check our conditions, so we need to do liner. Is it linear? So look at the scatter plot and the residual plot. What we'll find is this, is that the scatter plot shows a linear pattern, so that's good. For the residual plot, there's no obvious leftover curvature, and there's some standard scatter, even though we do notice that the residuals are negative when x is the value of 2. But we're fine for linear. For independence in this, all the flowers were in different vases. Knowing the hours of freshness for one flower shouldn't provide additional information about hours of freshness for the other. We set up this experiment fairly and adequately, so independence is met. For normalcy, look at that residuals of the histogram plot. And we're going to notice here it says the residuals do not show any skewness or outliers in that histogram, so we can assume approximately normal. For equal variance, we're going to reference that residual plot again and look at the x values when they were 1, 2, 3, and 4, and we're looking for nice scatter above and below and that it's consistent and constant. If we do look at that, we're going to say that although the variability of residuals is not constant at each value of x, there's no systematic pattern such as increasing variation as the x's increase themselves. So we're okay with the equal variance. And then lastly, for random, the flowers are randomly assigned to the treatments. Conditions are met, so we can construct the interval. The do portion, let me show you the hand calculations and actually show you the calculator to get the confidence interval for the slope. So again, our confidence interval is in this format, and I do want to find the degrees of freedom for T star. So degrees of freedom is going to be our sample size minus 2. So degrees of freedom are 10. Now, to find the critical value for this, remember, do not reference the computer output and look for their T value. We want to compute our own, so it's a 0.995 for the area under the curve at 10 degrees of freedom, which will give us a T star of 3.169. Now let's just put in the slope and standard error for the slope. When we do that, our calculation is going to come out to be this particular confidence interval for the slope. Now, if we use the calculator, it's actually quite easy. We are going to go to Stat and Tests. On Stat Tests, we are looking for letter G down here. It's linear regression T interval. So you're going to have to scroll quite a ways. When you click on that, just look at the prompts. They want to know the X list and your Y list. So you're going to put all your data of X's in list 1 and Y's in list 2. Frequency is just 1. Put in the confidence interval level you want, and then do calculate. You're going to notice right here that we actually have the same answer as if we calculated it by hand. What I would definitely write down here is this is our B, or our slope estimate. Here's our degrees of freedom. And then be very careful. This S value here is the standard error of the residuals. This is not the standard error of the slope that we actually use right here. So if you write it down, make sure you don't put it back in the confidence interval that way. And then you are going to see your linear correlation and your coefficient for the determination, along with the values that gets you your least squares regression line. Let's make a conclusion. We can say we're 99% confident that the interval from 9.04 to 21.36 captures the slope of the true regression line relating hours of freshness Y to the amount of sugar X. Part B in here asks us, would you feel confident predicting the hours of freshness if 10 tablespoons of sugar are used? I really like this as a great review question, again from Chapter 3. Remember, in our experiment, we're using 0, 1, 2, and 3 tablespoons of sugar. So if we were to use 10 tablespoons of sugar, our response should be this: no, this would be extrapolation. We have no idea if the linear form will continue beyond X of being 3 tablespoons. So at some point, there will be more sugar than flours could actually handle. So don't forget the word extrapolation. Remember, if you don't remember it was extrapolation, don't use it. You don't have to. You can just talk about this in the scenario in that it's beyond our X input values. Last example, talking about tipping at a buffet. Do customers who stay longer at a buffet give larger tips? Charlotte, an AP Stat student who worked at an Asian buffet, decided to investigate this question for her second semester project. While she was doing her job as a hostess, she obtained a random sample of receipts, which included the length of time in minutes that the party was there and the amount of tip in dollars. Do these data provide convincing evidence that the customers who stay longer have larger tips? Well, here is her actual data that she collected. Here is the scatter plot of the data. And right here we are seeing, it looks like residuals to z-scores. Folks, this is a normal probability plot. And we have the computer output for that. Part A says, here's a scatter plot of data with a least squares regression line. Describe what this tells you about the relationship of the two variables. Remember, that just means DOFs. So in terms of DOFs, we could say that this is a weak positive linear association between the length of stay and the amount of tip. Might that tell us about the relationship? Well, we might tell us that people who stay longer tend to give larger tips. We could do a further analysis into this if we wanted to know more. Part B, what is the equation of the least squares regression line for predicting the tip from the amount of the stay? We're just going to go back to the computer output. Again, this is great review for writing least squares regression lines. From that, we saw that our y hat, or the amount of predicted tip, our y-intercept, and our slope, and x is the amount of stay. For part C, let's interpret the slope and y-intercept. The slope in this case would just say that as x goes up by one variable, it's how much we would expect y to change. So in context, we could say for the slope, for each additional minute a party stays at the buffet, the least squares regression line predicts an increase in the tip of about 3 cents. The y-intercept in this case just says the model predicts a party that stays at the buffet for 0 minutes will leave about a $4.53 tip. This seems unreasonable, one, because it definitely is extrapolation. We have no data that's even at a time limit of 0 or close to it.